Right now, you are racing through space at over 1 million miles per hour. Your entire galaxy, everything you have ever known, is being dragged towards something massive, something we cannot see. In the 1970s, scientists noticed hundreds of galaxies were moving in the same direction, pulled by an invisible force. They called it the Great Attractor. Hidden behind a wall of dust and stars, this cosmic mystery waits in the darkness. If you are enjoying this journey into the unknown, hit that like button and subscribe. Prepare yourselves. We begin. Everything beneath your feet is moving faster than a bullet. Earth spins at over 1,000 miles per hour, carrying you through space whether you feel it or not. Every single second, our planet travels 18 miles along its path around our star. That star itself races through the galaxy at 500,000 miles per hour, yet you sense none of this motion. Your brain cannot detect movement at cosmic scales. When you stand still, you assume the universe stands still with you. This is a confirmed illusion. Scientists measure motion by observing other galaxies and comparing their positions over time. What they discovered changed everything we thought we understood about our place in space. The entire Milky Way galaxy, with its 200 billion stars, is being pulled through the universe at breathtaking speed. Picture a massive ocean current dragging everything in its path. We are caught in that current, moving at over 1 million miles per hour toward a distant point in space. This movement has continued for billions of years without pause. How do astronomers know this? They study something called peculiar velocity. Imagine the universe expanding like a balloon being inflated. Galaxies should move away from each other smoothly as space stretches. Instead, certain galaxies show extra motion on top of that expansion. This extra speed reveals hidden forces at work. In the late 1970s, researchers noticed our galaxy was not following the expected pattern. Something massive was influencing our path. They measured the cosmic microwave background radiation, the faint glow left over from the Big Bang. When they analyzed this ancient light, they found a telltale signature. The radiation appeared slightly hotter in one direction and cooler in the opposite direction. This dipole pattern confirmed our motion through space. The numbers were staggering. Our local group of galaxies, including the Milky Way and Andromeda, moves at 631 miles per second. That is fast enough to cross the United States in just 6 seconds. Most people assume galaxies drift slowly like clouds. The reality is far more violent. Think of it like being inside a moving train with no windows. You cannot see the landscape rushing past. You feel no wind or vibration. Yet when you finally look outside, you realize you have been traveling at incredible speed the entire time. Our galaxy is that train, and space itself provides no reference point to sense the journey. This discovery raised an immediate question. What force could be powerful enough to drag thousands of galaxies across such vast distances? Gravity seemed the obvious answer. Somewhere out in the darkness, an enormous concentration of mass had to exist. Something big enough to affect the motion of structures hundreds of millions of light years away. Scientists began searching for this cosmic engine. They studied galaxy distributions, mapped out dense regions, and calculated gravitational effects. What they found went beyond their predictions. The pull was too strong for any visible structure to explain. Something far stranger was happening in the depths of space, something that would challenge our understanding of the universe itself, and the mystery was only beginning to unfold. The first clue came from an astronomer who refused to accept the standard model. In the early 1980s, Alan Dressler was measuring the speeds of galaxies in our cosmic neighborhood. He expected to find random motion, like bees drifting in different directions. Instead, he discovered a pattern that should not exist. 400 galaxies were all moving the same way. They traveled together like a vast school of fish, pulled by an invisible current. The direction was clear, the speed unmistakable. Every measurement pointed toward a specific region of space. roughly 200 million light-years away. Dressler called this mysterious force the Great Attractor. His colleagues were skeptical at first. The idea seemed too dramatic, too simple. Galaxies this far apart should not behave like they were connected by cosmic ropes. Space was supposed to be more chaotic, more random. Yet the data kept confirming the same result. Hundreds of independent observations showed identical motion. The evidence came from studying redshift, a measurement that reveals how fast objects move through space. When a galaxy moves away from us, its light stretches toward the red end of the spectrum. When it moves toward us, the light shifts toward blue. By measuring these shifts carefully, astronomers can calculate exact velocities. This is a confirmed scientific technique used throughout modern astronomy. What made the Great Attractor discovery so shocking was the sheer scale of coordination. Imagine standing in a massive crowd where everyone suddenly starts walking in the same direction without being told. That synchronized movement would demand an explanation. The same logic applied to galaxies. Something enormous had to be orchestrating this cosmic dance. Dressler calculated the mass required to create such powerful attraction. The numbers climbed into the tens of thousands of galaxy masses. Think of it like a magnet strong enough to pull cars from 10 miles away. The force field had to extend across distances that would take light 200 million years to cross. Nothing in the known universe matched that description. Teams of astronomers around the world began studying the same region of space. They used different telescopes, different methods, different approaches. All of them arrived at the same conclusion. Our galaxy was falling towards something massive. The Great Attractor was real. But here was the problem. When they pointed their most powerful telescopes at the predicted location, they saw nothing unusual. No obvious concentration of galaxies appeared. No bright cluster dominated the area. The region looked ordinary, almost boring. This made no sense whatsoever. How could something invisible pull thousands of galaxies across such vast distances? The mass had to be somewhere. Matter cannot hide from gravity. If the Great Attractor contained tens of thousands of galaxy masses, that material should be obvious. Scientists began proposing wild theories to explain the discrepancy. Perhaps dark matter, the mysterious substance that makes up most of the universe, was concentrated in that region. Maybe the calculations were wrong, or the measurements flawed. Some wondered if our understanding of gravity itself needed revision at cosmic scales. The truth was stranger than anyone imagined. Our own galaxy was hiding the answer, creating a blind spot at exactly the wrong location. Picture trying to see a distant mountain while standing inside a dense forest. The trees closest to you block your view of everything beyond. Our galaxy creates the same problem for astronomers. The Milky Way sits between us and the Great Attractor like a cosmic curtain made of stars, gas, and dust. This blind spot has a name. Scientists call it the zone of avoidance. The name sounds ominous, almost like a place too dangerous to explore. In reality, it describes a frustrating limitation. Roughly 20% of the entire sky remains hidden from our most powerful optical telescopes. That missing piece happens to contain the answer to one of astronomy's biggest mysteries. The problem comes from our location inside the galactic plane. Imagine looking at a dinner plate edge-on instead of from above. You see the rim clearly, but the center is obscured. We live inside that plate, trying to peer through millions of stars and vast clouds of cosmic dust. Every line of sight toward the galactic center passes through this material. Dust particles in space are incredibly tiny, smaller than smoke particles in air. Yet they pile up over distances of thousands of light years. Think of it like fog that starts thin but becomes opaque when you try to look through miles of it. The cumulative effect blocks visible light completely. Stars that should shine brightly appear dim or vanish entirely. This is a confirmed observational challenge that has plagued astronomy for over a century. In 1878, an astronomer named Richard Proctor noticed that certain parts of the sky had very few visible galaxies. He called it the zone of few nebulae. Later observations revealed the truth. The galaxies were there all along. We simply could not see them. The Great Attractor sits deep within this hidden zone. From Earth, we look toward the constellations Triangulum, Australe, and Norma when we search for it. Both lie along the Milky Way's galactic plane. Every telescope pointed in that direction encounters the same wall of obscuring material. The timing could not be worse. Astronomers have tried various tricks to peek behind the veil. Some use longer exposures, hoping to capture faint light that makes it through the dust. Others search for gaps in the obscuration, narrow windows where the blocking material thins out temporarily. Neither approach works well enough to map the region properly. The dust does more than block light. It also scatters and absorbs specific wavelengths, changing what we can detect. Blue light gets scattered more than red light, creating false impressions about the color and temperature of distant objects. Even when faint galaxies appear, their properties remain uncertain. Are we seeing them accurately or through a distorting filter? Scientists estimate that approximately 10% of the sky near the galactic plane remains effectively invisible to optical surveys. Within that zone, we might be missing entire galaxy clusters. Thousands of galaxies could be hiding in plain sight, their light blocked by nothing more than cosmic dust. The Great Attractor occupies the worst possible location within this forbidden zone. Just when astronomers need clear observations most, nature delivers maximum obscuration. Yet something even stranger was about to be discovered. Scientists faced a seemingly impossible problem. They needed to observe galaxies hidden behind walls of dust that blocked all visible light. Traditional telescopes were useless. The solution came from a different part of the electromagnetic spectrum, wavelengths invisible to human eyes. Infrared light behaves differently than visible light when encountering cosmic dust. Think of infrared as a longer wavelength that can slip between dust particles more easily, like water flowing through a coarse filter. While visible light gets scattered and absorbed, infrared radiation passes through with less interference. This property makes infrared telescopes perfect for exploring the zone of avoidance. In the late 1980s, astronomers launched the Infrared Astronomical Satellite. This confirmed space-based observatory could detect heat radiation from distant galaxies. When they pointed it toward the Great Attractor region, objects invisible to every optical telescope suddenly appeared. Dozens of galaxies emerged from the darkness. The images were crude compared to modern standards. Galaxies appeared as fuzzy blobs rather than detailed spirals. Yet even these rough observations provided crucial information. Scientists could now count galaxies, estimate their distances, and measure their properties. The Great Attractor region was finally revealing its secrets. Radio waves provided another window into the hidden zone. These wavelengths are even longer than infrared, allowing them to pass through dust with almost no obstruction. Radio telescopes detect emissions from neutral hydrogen gas, a substance abundant in galaxies. By mapping hydrogen signals, astronomers can locate galaxies even when no light escapes. Picture it like using sonar instead of vision to explore a dark cave. You cannot see the cave walls, but sound waves bounce back and reveal their location. Radio astronomy works on similar principles. The technique uncovered hundreds of galaxies lurking behind the Milky Way's obscuring disk. One discovery stood out among all others. The Norma cluster appeared in infrared and radio observations like a ghost materializing from fog. This massive collection of galaxies sits almost exactly where scientists predicted the Great Attractor should be located. The cluster contains hundreds of large galaxies packed into a relatively small volume of space. Many of these galaxies are old, filled with ancient stars that formed billions of years ago. Even more dramatic, many galaxies in the Norma cluster are colliding with their neighbors. When galaxies crash together, they release enormous amounts of energy. Some of this energy emerges as radio waves, making the collisions visible to radio telescopes. The cluster was a cosmic battleground, though played out in slow motion over millions of years. X-ray telescopes added another layer to the picture. Hot gas trapped between galaxies emits X-rays as it heats up to millions of degrees. The Norma cluster showed strong X-ray emissions, confirming the presence of massive amounts of material. Scientists could finally start calculating the total mass of the structure. Yet something remained wrong with the numbers. The mass they could detect, even adding up all the visible galaxies and hot gas, fell short of what was needed. The Norma cluster appeared impressive, containing perhaps 1,000 trillion times the mass of our star. That sounds enormous, until you compare it to the gravitational pull being measured. The attraction felt by our galaxy and its neighbors required 10 times more mass than what observations revealed. Where was the missing material hiding? The answer would reshape our understanding of the universe itself. Imagine weighing an invisible elephant. You cannot see it, but you can measure how the floor bends beneath its feet. Astronomers use the same logic to study the Great Attractor. They observe how galaxies move, then calculate backward to determine what mass could create that motion. The results pointed to a staggering conclusion. Something containing the mass of tens of thousands of galaxies had to exist in that region. The gravitational field extended outward like ripples from a stone dropped in a cosmic pond. Galaxies, hundreds of millions of light years away, felt the pull. Our local group responded to that attraction, accelerating toward it at over 1 million miles per hour. Scientists refined their measurements throughout the 1980s and 90s. They studied galaxy motions with increasing precision, using better instruments and more sophisticated techniques. The pattern remained consistent. A massive concentration of matter occupied the zone of avoidance. Yet visible matter accounted for only a fraction of the required mass. This discrepancy revealed something profound about the universe. Most of the matter creating gravitational effects cannot be seen with any telescope. Astronomers call this invisible substance dark matter. This is a confirmed component of modern cosmology, detected only through its gravitational influence. Regular matter, the stuff that makes stars and planets and people, represents less than 20% of all matter in the universe. Dark matter does not emit light. It does not absorb light. It passes through regular matter like a ghost walking through walls. The only way to detect it is by observing how its gravity affects visible objects. Think of it like wind moving through a forest. You cannot see the wind itself, only the swaying trees that prove its existence. The Great Attractor region likely contains enormous quantities of dark matter. This invisible material creates the powerful gravitational field that pulls on surrounding galaxies. The visible galaxies we detect, like the Norma cluster, are merely markers indicating where dark matter has gathered. They are signposts pointing towards something much larger. Scientists estimate that dark matter outweighs visible matter by a ratio of 5 to 1 throughout the universe. In regions like the Great Attractor, that ratio might be even more extreme. Vast halos of dark matter could surround every galaxy cluster, extending far beyond the visible boundaries. When galaxies form, they settle into these dark matter structures, like fruit forming on invisible branches. This explanation solved part of the mystery while creating new questions. How does dark matter distribute itself? What creates these massive concentrations? Why do some regions become super dense while others remain nearly empty? Theoretical models suggested that dark matter formed structures first, shortly after the Big Bang. Regular matter followed later, falling into the gravitational wells created by dark matter. Over billions of years, these wells deepened as more material accumulated. The Great Attractor represents one such well, grown to extraordinary size. Yet, even accounting for dark matter, scientists still struggled to explain every observation. The pull felt by distant galaxies seemed stronger than any single concentration of matter could produce. The motion of our local group did not point precisely toward the Norma cluster. Something else was influencing the cosmic flow. Researchers began suspecting that the Great Attractor might be part of an even larger structure. Perhaps what they had discovered was just one piece of a more complex puzzle. The search was expanding beyond a single gravitational center toward understanding entire networks of cosmic attraction. What they would find next defied every prediction. In 2014, a team of astronomers announced a discovery that changed our cosmic address forever. They had mapped the motion of galaxies across 500 million light-years of space. The pattern revealed something extraordinary. The Great Attractor was not the final destination. It was merely a valley in a much larger gravitational landscape. Think of water flowing downhill toward a lake. Multiple streams converge from different directions, all pulled by gravity toward the lowest point. Galaxies behave similarly. They flow along invisible pathways defined by dark matter distribution. When astronomers traced these cosmic rivers backward to their source, they discovered an immense basin of attraction. This structure dwarfed anything previously imagined. It contained roughly 100,000 large galaxies spread across 500 million light-years. That distance is so vast that light takes 500 million years to cross from one side to the other. Our entire galaxy, everything we can see in the night sky, represents just one tiny droplet in this cosmic ocean. The research team gave this superstructure a Hawaiian name, Laniakea. The word translates as immense heaven or immeasurable sky. Polynesian navigators used stars to cross the Pacific Ocean, finding their way through vast emptiness using celestial knowledge. The name honors their legacy while describing our place in an even vaster cosmic sea. Laniakea is a confirmed basin of gravitational attraction. Galaxies throughout this region flow inward toward a central point. The Great Attractor sits near the heart of this basin, acting as a focal point where matter streams converge. Our Milky Way lies on the outer edge, slowly falling toward the center like a marble rolling down the inside of a bowl. Mapping this structure required measuring the distances and velocities of thousands of galaxies. Each measurement took careful observation and complex calculations. Scientists looked for peculiar velocities. The extra motion galaxies show beyond universal expansion. By charting these motions, they could trace the gravitational flows throughout the region. Picture watching leaves floating on a river. By observing which direction each leaf moves, you can determine where the current flows and locate deeper channels. Galaxies serve as similar markers. Their paths reveal the underlying structure of space, showing where mass concentrates and where voids lie empty. The discovery of Laniakea answered some questions while raising others. It explained why the Great Attractor alone could not account for our galaxy's motion. We were responding to the combined pull of an entire supercluster, with the Great Attractor marking just one concentration within a larger network. The gravitational influence stretched far beyond any single cluster. Yet, Laniakea itself appeared to be moving. Observations showed the entire supercluster drifting toward another concentration of matter even farther away. Something beyond Laniakea was exerting its own pull. The cosmic hierarchy extended to scales that challenged comprehension. Scientists identified this distant attractor as the Shapley concentration. Located roughly 650 million light-years from Earth, this structure represents one of the largest collections of matter in the observable universe. It contains thousands of galaxies, organized into numerous clusters. The mass involved reaches truly staggering proportions. Laniakea appears to be falling toward Shapley, just as we fall toward the Great Attractor within Laniakea. These nested structures create a cascade of motion across cosmic scales. Every level of organization influences the next. Our journey through space involves multiple forces pulling simultaneously from different directions. The story was becoming clear, though far more complex than anyone anticipated. The Shapley concentration pulls on Laniakea with relentless gravity, This distant supercluster contains roughly 10 times more mass than our home structure. Think of it as a cosmic drain, where matter from vast regions of space flows inward. Everything within billions of light-years feels its influence to some degree. Measuring the Shapley concentration's effects requires incredible precision. Astronomers study the motions of galaxies across enormous distances, searching for subtle deviations from expected expansion. These peculiar velocities reveal the tug-of-war between different gravitational centers. The data confirmed that Laniakea, as a whole, moves towards Shapley at hundreds of miles per second. This creates a strange situation. We fall toward the Great Attractor. The Great Attractor falls toward the broader Laniakea basin, and Laniakea itself falls toward the Shapley concentration. Each motion happens simultaneously, like waves overlapping in a turbulent sea. Our total velocity through space represents the sum of all these influences combined. Scientists now understand that basins of attraction exist at multiple scales throughout the universe. Small groups merge into clusters. Clusters connect into superclusters. Superclusters might be components of even larger structures. The cosmic web extends as far as telescopes can see, possibly continuing beyond the observable universe. These structures formed through a process that began shortly after the Big Bang. Tiny fluctuations in the density of matter created the seeds for future galaxies. Regions slightly denser than average pulled in more material through gravity. Over billions of years, these small advantages compounded. Dense areas grew denser, while sparse regions became increasingly empty. Think of how cities form along rivers and coastlines. People gather where resources concentrate. The pattern reinforces itself as more people attract even more. Galaxies follow similar logic. They cluster where dark matter first accumulated. Those clusters attract additional galaxies. The process continues across cosmic timescales. The Great Attractor emerged as one focal point in this grand pattern. Material flowing through Laniakea converges there, creating a gravitational well that deepens with each passing million years. Galaxies in the Norma cluster represent visible markers of this accumulation. Dark matter halos surrounding them contain far more mass. Yet recent research revealed something even more surprising about our cosmic neighborhood. The pull we feel does not come solely from attraction. Another force was acting on our galaxy from the opposite direction, a force that pushes rather than pulls. In 2017, astronomers identified a vast void on the far side of the Milky Way from the Great Attractor. This region, largely empty of galaxies, creates what scientists call a repelling effect. Imagine standing between a magnet and an empty space. The magnet pulls you forward, while the emptiness offers no counterpull, effectively pushing you away from itself. This void received the name dipole repeller. The term describes how it works together with the Shapley attractor to create a two-sided force. We are pulled in one direction and pushed from behind. Both influences contribute roughly equally to our motion through space. The discovery fundamentally changed how scientists understood galactic flows. Voids are common throughout the universe. These regions contain very few galaxies, creating vast empty bubbles in the cosmic web. The largest known voids stretch across 300 million light-years or more. Inside these regions, almost nothing exists. An observer placed in the center of a void would see darkness in every direction, with galaxies appearing only as distant specks near the horizon. The dipole repeller appears to be a particularly large void. Its influence extends across enormous distances, creating pressure that pushes the local group away. Combined with the pull from Shapley and the Great Attractor, this creates our observed motion through space. Something more complex was shaping the cosmos than simple attraction. Voids do not actually push. That description simplifies a more subtle reality. Gravity always attracts, never repels. Yet, regions with less mass create effects that appear like repulsion when viewed from the right perspective. Understanding this requires thinking about gravity differently than we usually do. Picture yourself standing in a room with people on all sides. Everyone pulls on you with gravity equally in every direction. The forces cancel out, leaving you stationary. Now imagine half the people leave from one side of the room. The remaining people on the other side create an imbalance. Their pull, no longer cancelled, moves you toward them. It appears as if the empty side pushed you away. The dipole repeller works on this principle at cosmic scales. In regions filled with galaxies, matter pulls from all directions simultaneously. These forces largely balance out. When a void exists, one direction contains far less mass. The galaxies on the opposite side create an unopposed pull. Objects near the void appear to be repelled by the emptiness, when actually they are attracted more strongly toward the denser regions. This is a confirmed mechanism in cosmology. Scientists call it gravitational pressure or gravitational repulsion, though both terms can be misleading. Nothing actively pushes. The effect emerges from unbalanced attraction. Think of it like water pressure in reverse. High pressure pushes water toward low pressure. In gravity, low-density areas appear to push objects toward high-density areas. The dipole repeller sits roughly 220 million light-years from Earth. Its location places it almost directly opposite to the Shapley concentration. This alignment is not coincidental. The cosmic web arranges matter into filaments and walls, with voids occupying the spaces between. The Great Attractor and Shapley lie along one filament. The dipole repeller represents a void between different filaments. Mapping the dipole repeller proved challenging. You cannot photograph emptiness. Astronomers instead studied galaxy flows, looking for regions where motion diverged outward. These divergence patterns indicated where underdense regions existed. Computer models then reconstructed the three-dimensional structure of the void. The results showed a massive region containing very few galaxies. While not completely empty, the dipole repeller holds far less matter than average space. Estimates suggest it contains perhaps 10% of the normal galaxy density. That shortage creates a gravitational deficit large enough to influence our motion. Recent observations have started to detect the few galaxies that do exist within the void. Radio telescopes can find these isolated objects by detecting their hydrogen emissions. Each discovery helps confirm the void's extent and properties. The galaxies appear spread out, separated by vast distances with nothing between them. Living in such a void would be lonely. An observer on a planet in one of these sparse galaxies would see almost nothing when looking at the night sky. The nearest neighboring galaxy might be tens of millions of light-years away. Most of the visible universe would appear dark and empty. Only by looking toward the void's edges would distant galaxy clusters become visible. The dipole repeller contributes roughly half the force, affecting our local group's motion. The other half comes from the combined pull of the Great Attractor and Shapley concentration. Together, these influences explain both the direction and speed of our journey through space. The mystery that puzzled astronomers for decades finally had a complete answer. Our galaxy moves at over 1 million miles per hour because we are being pushed and pulled by the largest structures in the universe. We fall toward concentrations of mass while being pushed away from regions of emptiness. The balance between these forces determines our path, yet this still was not the full story. The universe refuses to stay still. Every structure we have discussed, from the Great Attractor to the Shapley concentration to the dipole repeller, exists in a cosmos that is expanding. This expansion changes everything about how these gravitational forces work over time. Understanding our ultimate fate requires grasping this cosmic stretching. In 1929, Edwin Hubble made a discovery that revolutionized astronomy. He observed that distant galaxies were moving away from us, and the farther away they were, the faster they receded. This relationship, now called Hubble's law, revealed that space itself expands. Galaxies are not flying through space like rockets. Rather, new space continuously appears between them, pushing them apart. Think of dots drawn on a balloon. As you inflate the balloon, The dots move away from each other, even though they stay fixed to the surface. The expansion of the material between them creates the separation. Space behaves similarly. Every region stretches, carrying galaxies along with it. This expansion works against gravity. While the Great Attractor pulls us closer, universal expansion simultaneously pushes us apart. Over short distances, gravity wins easily. Our galaxy will never be torn apart by expansion. The gravitational bonds holding stars together are far too strong. Even within galaxy clusters, gravity maintains control. Yet at larger scales, expansion begins to dominate. Structures like Laniakea are not gravitationally bound. The supercluster will not hold together forever. Eventually, expansion will overcome the internal gravitational attraction. Laniakea will dissolve as its component parts drift away from each other. This process is already happening, just very slowly. Scientists calculate that Laniakea represents a temporary structure. It flows together now because matter is still falling into the gravitational basin. Yet, in the distant future, expansion will reverse this trend. The supercluster will break apart into separate pieces. Something makes this process even more dramatic. In the late 1990s, astronomers discovered that universal expansion is accelerating. Instead of slowing down over time as gravity pulls everything together, the expansion rate increases. This unexpected finding earned its discoverers the Nobel Prize in Physics. The cause remains mysterious. Scientists attribute the acceleration to dark energy, a hypothetical force that permeates all of space. Unlike dark matter, which clumps and creates gravity, dark energy appears uniformly distributed. It acts as a kind of cosmic pressure, pushing space to expand faster and faster. Dark energy represents roughly 70% of all energy in the universe. This is a confirmed observation based on multiple independent measurements. Regular matter makes up less than 5%. Dark matter accounts for around 25%. Dark energy dominates everything else combined. As dark energy strengthens over billions of years, it will gradually tear apart every structure in the universe. First, superclusters like Laniakea will dissolve. Then galaxy clusters will separate. Eventually, even our local group might break apart as Andromeda and the Milky Way drift beyond each other's gravitational reach. This fate lies trillions of years in the future. For now, we continue falling toward the Great Attractor. Our journey will persist for billions of years before expansion changes the dynamics. We will travel immense distances across the cosmos, pulled by gravity toward concentrations of matter, yet we will never arrive. The expansion of space ensures that the Great Attractor remains forever out of reach, receding as we approach. Our cosmic journey has no destination, only endless motion through an expanding void. The question becomes what happens next. Scientists project our future by running computer simulations. These models incorporate everything we know about gravity, dark matter, dark energy, and cosmic expansion. They track the motion of millions of simulated galaxies across billions of years. The predictions paint a strange picture of our cosmic destiny. For the next few billion years, our galaxy will continue moving toward the Great Attractor region. We will cover enormous distances, crossing perhaps 100 million light-years of space. Yet the Great Attractor itself will also be moving, pulled toward the Shapley concentration. We chase a target that constantly relocates. Think of trying to catch a train that accelerates faster than you can run. You might close the distance temporarily, but eventually the gap will start widening. Dark energy plays the role of the accelerating train. It ensures that the farthest structures remain perpetually beyond our reach. Around the same time we are pursuing the Great Attractor, another cosmic event will unfold. The Milky Way and Andromeda galaxies are heading toward each other at roughly 70 miles per second. In approximately 4 billion years, these two massive spirals will collide. The impact will be spectacular. Galaxy collisions are not like car crashes. Stars within each galaxy are separated by such vast distances that actual stellar collisions remain incredibly rare. Instead, the galaxies will pass through each other like swarms of bees interpenetrating. Gravity will scramble their orbits, creating long tails of stars flung into space. Over hundreds of millions of years, the two galaxies will merge into a single elliptical galaxy. This new combined structure will contain all the stars from both original galaxies. Some scientists have dubbed the future merger Milkomeda or Milkdromeda. Whatever we call it, the result will be dramatically different from our current spiral form. This merger happens while we still fall toward the Great Attractor. The combined gravity of the merged galaxy will create an even stronger pull toward Laniakea's center. Our motion will continue, perhaps even accelerate temporarily, yet expansion will be working against us the entire time. By roughly 10 billion years from now, dark energy will have pushed most structures outside Laniakea beyond our gravitational reach. The Shapley concentration will recede to unreachable distances. Distant superclusters will disappear beyond the cosmic horizon as space between us expands faster than light can travel. Our local group, possibly merged with other nearby galaxies, will become isolated. We will inhabit a cosmic island surrounded by expanding emptiness. The great cosmic flows that currently connect us to distant structures will cease. We will drift alone through an increasingly empty universe. This isolation will deepen over trillions of years. Eventually, even the cosmic microwave background radiation will be stretched to undetectable wavelengths. Future astronomers living on planets around distant stars will see almost nothing when they look at the sky. The evidence for the Big Bang, for universal expansion, for everything beyond their local galaxy group will have vanished. They might assume the universe consists only of what they can see. Their entire cosmos will appear to be a single island of matter floating in infinite darkness. The rich structure we observe today, with its superclusters and voids and great attractors, will be lost to observation. Only ancient records, if any survive, will preserve knowledge of the larger universe. Our current era represents a special time. We can observe the cosmic web in all its complexity. We can measure flows across hundreds of millions of light years. We can detect the pull of the Great Attractor and the push of the dipole repeller. Future generations will miss this view entirely. The cosmic web represents the largest known structure in the universe. It organizes matter across billions of light years, creating patterns that look almost biological under certain visualizations. Filaments of galaxies connect like neurons in a vast cosmic brain. Between them lie the voids, empty regions where almost nothing exists. This structure emerged from the early universe through a process that began 380,000 years after the Big Bang. Before that moment, space was too hot and dense for atoms to form. Everything existed as a plasma of particles bouncing off each other continuously. Light could not travel far before scattering off this material. Then the universe cooled enough for atoms to form. Suddenly, light could travel freely through space. This moment, called recombination, released the cosmic microwave background radiation we still detect today. That ancient light carries information about tiny density variations that existed in the early universe. These variations were incredibly small, just one part in 100,000. Imagine a perfectly smooth surface with bumps that rise only 1 millimeter per 100 meters. That describes how uniform the early universe appeared. Yet these tiny fluctuations contained the seeds for every structure we see today. Regions slightly denser than average had slightly stronger gravity. They pulled in nearby material a bit faster than average regions. This increased their density further, which increased their gravity more. The process fed back on itself in a loop that continued for billions of years. Dense areas grew denser. Sparse areas grew emptier. Think of cream separating from milk. Initially, the mixture appears smooth. Over time, density differences become more pronounced. Fat globules cluster together while watery regions form between them. The universe underwent similar separation, though driven by gravity instead of molecular forces. Dark matter played a crucial role in this process. Because dark matter does not interact with light or regular matter except through gravity, it could begin clumping earlier than normal matter. The dark matter structures formed first, creating gravitational wells. Regular matter followed later, falling into these pre-existing patterns. By the time the first stars formed, roughly 100 million years after the Big Bang, the cosmic web was already taking shape. Galaxies assembled along dark matter filaments. They avoided voids where dark matter remained sparse. This distribution persists today, refined and amplified by billions of years of gravitational evolution. The Great Attractor represents one node in this vast network. Material flows along filaments towards such nodes, creating concentrations of matter. Other flows avoid certain regions, allowing voids to expand. The dipole repeller marks one such underdense zone. Together, these features create the gravitational landscape through which we move. Recent computer simulations can recreate this process. Scientists input the initial conditions from the early universe, then let virtual gravity evolve the system forward. The results match real observations remarkably well. Simulated cosmic webs develop filaments, clusters, and voids in patterns similar to what telescopes reveal. These simulations confirm our understanding of how structure forms. They validate the role of dark matter in shaping the universe. They demonstrate how tiny initial fluctuations can grow into the massive structures we observe. The match between theory and observation provides strong confidence in our cosmological models. Yet mysteries remain. Some observed structures appear larger than simulations predict. The Laniakea supercluster, for example, seems more extensive than models suggest should exist. The Shapley concentration contains more mass in a smaller volume than seems likely. These discrepancies hint that we might be missing something. Perhaps our understanding of dark matter is incomplete. Maybe dark energy behaves differently than we assume. The initial conditions from the early universe might have been slightly different than we think. The truth waits to be discovered. Astronomers continue mapping the cosmic web with increasing precision. Each new galaxy survey extends our view deeper into space and farther back in time. The most ambitious projects aim to catalogue millions of galaxies across billions of light years. Every measurement helps refine our understanding of how the universe is structured. One recent survey discovered something unexpected in the zone of avoidance. Using radio telescopes that can penetrate the dust of the Milky Way, researchers found hundreds of previously unknown galaxies. These objects had been hiding behind our galactic disk, completely invisible to optical telescopes. Their discovery filled in crucial gaps in our maps. Many of these hidden galaxies belong to a structure called the Vela supercluster. This massive concentration of matter sits partially behind the zone of avoidance, making it difficult to study. Early observations suggested it might be connected to the Great Attractor region. The new radio surveys confirmed this suspicion. The Vela supercluster extends the known structure of the Great Attractor. Think of it as discovering that a lake you were studying actually connects to a larger system of waterways. The gravitational basin is bigger than previous estimates suggested. More mass concentrates in that region than we could see before. This discovery helps explain some of the remaining mysteries about our motion. The pull we feel might come from multiple connected structures rather than a single concentration. The Great Attractor, the Norma cluster, and the Vela supercluster could form parts of an even larger complex. Together, they create gravitational effects stronger than any individual component. Radio astronomy has become essential for exploring the zone of avoidance. The Meerkat telescope array in South Africa has proven particularly valuable. Its 64 dishes work together to create detailed radio maps of the sky. They can detect faint hydrogen emissions from galaxies millions of light years away, even when those galaxies hide behind dense dust clouds. Each discovery adds pieces to the cosmic puzzle. Scientists now estimate that as many as 1,000 galaxies might remain hidden in the deepest parts of the zone of avoidance. Finding and cataloguing these objects will take decades of patient observation, yet each new detection improves our understanding of the mass distribution near the Great Attractor. Infrared surveys complement radio observations. The James Webb Space Telescope, launched in 2021, can peer through dust with unprecedented clarity. Its infrared instruments reveal galaxies invisible to previous telescopes. Early observations have already uncovered new structures in regions thought to be well mapped. These combined observations create three-dimensional maps of the local universe. Scientists plot the positions of galaxies, calculate their distances, and measure their velocities. The resulting models show how matter flows through space. You can visualize streamlines, like currents in an ocean, showing the path each galaxy follows. The maps reveal that cosmic flows are more complex than simple attraction to a single point. Multiple attractors and repellers influence motion simultaneously. Galaxies follow curved paths determined by the combined gravitational field of all nearby structures. Some galaxies flow toward the Great Attractor, others move toward different nodes in the cosmic web. Our Milky Way follows one particular streamline in this complex flow. We are pulled toward the Great Attractor as part of the broader Laniakea Basin. Simultaneously, the dipole repeller pushes from behind. The Shapley concentration exerts its own distant influence. All these forces combine to determine our exact trajectory through space. Scientists compare this to weather patterns on Earth. Winds do not flow straight from high pressure to low pressure. Instead, they curve and swirl, influenced by planetary rotation, temperature differences, and geographical features. Cosmic flows show similar complexity, shaped by the distribution of matter across vast scales. Understanding these patterns helps us predict the future. By knowing our current motion and the forces acting on us, we can project where we will be millions or billions of years from now. The picture grows clearer with each observation. Galaxy collisions shape the evolution of the universe. When two galaxies approach each other, their mutual gravity initiates a complex dance. The interaction can last hundreds of millions of years, transforming both participants. The Great Attractor region hosts many such collisions happening right now. The Norma cluster, sitting near the heart of the Great Attractor, contains multiple galaxies in various stages of collision. Some are just beginning to interact, with tidal forces stretching their spiral arms. Others have merged completely, forming elliptical galaxies filled with old stars. Each collision releases tremendous energy. When galaxies collide, their stars rarely impact each other directly. Space between stars is so vast that stellar collisions remain extremely improbable. Think of throwing two handfuls of sand at each other. Individual grains almost never collide, but the overall patterns intermix. Galaxies behave similarly. What does collide are clouds of gas between the stars. These clouds slam together at millions of miles per hour, creating shock waves. The collisions compress the gas, triggering massive bursts of star formation. Regions that were quiet for billions of years suddenly ignite with new stars. Thousands of brilliant blue stars appear within a few million years. Radio telescopes can detect the aftermath of these collisions. The shock waves accelerate particles to incredible energies. These particles emit synchrotron radiation, a type of radio emission visible to specialized instruments. Colliding galaxies in the Norma cluster shine brightly in radio wavelengths, marking sites of violent interaction. X-ray observations reveal hot gas heated to millions of degrees by the collisions. This gas trapped between galaxies glows with X-ray light. The intensity indicates how much energy the collision released. Some systems emit more X-rays than all the stars in both galaxies combined. The power involved staggers the imagination. These collisions will eventually affect us. In roughly 4 billion years, the Milky Way will merge with Andromeda. our solar system will likely survive the encounter intact. The chances of any star actually hitting ours remain vanishingly small, yet the gravitational chaos will scramble stellar orbits throughout both galaxies. Our location within the merged galaxy will change dramatically. We might be flung toward the outskirts, far from the center, or we could spiral inward, ending up closer to the galactic core. The disk structure we inhabit will be destroyed. Stars will settle into a more spherical distribution, creating an elliptical galaxy. This process is happening throughout the Great Attractor region right now. Multiple galaxies merge, creating larger elliptical systems. These mergers contribute to the massive concentration of matter that creates the powerful gravitational pull. Over billions of years, small galaxies combine into larger ones. Those combine into larger ones still. The process builds the hierarchical structure we observe. Computer simulations can recreate galaxy collisions in remarkable detail. Scientists input the initial conditions, including the masses, velocities, and orientations of each galaxy. The simulation then calculates how gravity affects every particle over millions of years. The results show spiral arms being shredded, stars scattered into tidal tails, and eventual merger into elliptical forms. These simulations match real observations. The antennae galaxies, a famous colliding pair visible from Earth, look exactly like simulated collisions predict. The long streamers of stars, the regions of intense star formation, the distorted shapes, all emerge naturally from gravitational physics. This validates our understanding of how galaxy mergers work. The Great Attractor region will continue experiencing mergers for billions of years. Each collision adds more mass to the central concentration. The gravitational pull strengthens. More distant galaxies accelerate toward the region. The process feeds itself until dark energy eventually overpowers gravity. Understanding these collisions helps explain why the Great Attractor exists. Dark matter remains one of the deepest mysteries in modern science. We know it exists because of its gravitational effects. We can measure how much there is by observing galaxy rotations and cosmic flows. Yet we have never detected a single dark matter particle directly. This gap between inference and observation frustrates physicists. Multiple experiments search for dark matter particles. Some use incredibly sensitive detectors deep underground, shielded from cosmic rays. They wait for the rare moment when a dark matter particle might collide with a detector atom. So far, no confirmed detection has occurred. The particles, if they exist as we imagine, interact too weakly with regular matter to catch. Other experiments attempt to create dark matter in particle accelerators. By smashing protons together at enormous energies, scientists hope to produce dark matter particles that quickly decay into detectable byproducts. Again, no confirmed discoveries have emerged. The hypothetical particles remain elusive. This absence of direct detection bothers some scientists. Perhaps dark matter does not consist of particles at all. Maybe our understanding of gravity needs modification. At cosmic scales, gravity might behave differently than Einstein's equations predict. This would eliminate the need for dark matter altogether. Modified gravity theories exist and have their advocates. They successfully explain some observations, like galaxy rotation curves, yet they struggle to account for other phenomena. The cosmic microwave background radiation patterns, for example, require dark matter in standard models. Modified gravity alone cannot reproduce those observations. Most physicists remain convinced that dark matter particles exist. The evidence from multiple independent sources is simply too strong. Galaxy clusters contain more mass than visible matter can explain. Gravitational lensing reveals mass where no light exists. The formation of cosmic structure requires dark matter to seed galaxy formation. All these observations point toward invisible particles. The Great Attractor region likely contains enormous quantities of dark matter. Perhaps 10 times more dark matter than regular matter concentrates there. This invisible material creates the deep gravitational well that pulls surrounding galaxies inward. The visible galaxies we observe are merely markers floating in a vast, dark matter ocean. Think of icebergs. The visible portion above water represents only 10% of the total mass. The bulk remains hidden beneath the surface. Galaxies might work similarly. What we see represents a small fraction of what exists. Dark matter halos extend far beyond the visible boundaries, dominating the total mass. Measuring dark matter distribution remains challenging. Scientists use gravitational lensing to map where mass concentrates. When light from distant galaxies passes near massive objects, gravity bends the light path. This creates distortions in the images we receive. By analyzing these distortions, astronomers can reconstruct the mass distribution. Lensing studies of the Great Attractor region reveal exactly what theory predicts. Massive dark matter halos surround the visible galaxy clusters. The halos extend across millions of light years, creating deep potential wells. Regular matter falling into these wells forms the galaxies we observe. The visible universe traces the invisible scaffolding of dark matter. Future observations might finally detect dark matter particles directly. New experiments with greater sensitivity could catch the rare interactions. Upcoming space telescopes will map dark matter distribution with unprecedented precision. Each advance brings us closer to understanding this mysterious substance. Yet, even if we never detect dark matter directly, its existence seems certain. The gravitational effects are too consistent and too well measured to explain away. Something invisible holds galaxies together and shapes cosmic structure. That something pulls us toward the Great Attractor. The story of the Great Attractor reveals how little we truly see of the universe. Most of reality remains invisible. Dark matter outweighs visible matter 5-1. Dark energy dominates everything. The cosmic web spans distances. Light takes billions of years to cross. Our galaxy represents one tiny speck in an incomprehensibly vast cosmos. This realization has profound implications. It means our observations capture only a small fraction of what exists. When we look at the night sky, we see perhaps 5% of the matter present. The rest hides from our instruments, detectable only through gravity. We live in a universe where the invisible vastly outnumbers the visible. Consider what this means for our cosmic maps. Every galaxy catalogue remains incomplete. Every measurement of cosmic structure misses most of the mass. Scientists work with partial information, trying to reconstruct the full picture from limited clues. It is like trying to map an ocean by observing only the waves on the surface. The Great Attractor symbolizes this challenge perfectly. We know it exists because we feel its pull. We can measure its effects with precision, yet seeing it directly remains nearly impossible. Our own galaxy blocks the view. Dust obscures the region. The mass we need to observe exists as invisible dark matter. Everything conspires to keep the truth hidden. Yet through clever techniques and persistent observation, scientists have gradually unveiled the mystery. Infrared telescopes pierce the dust. Radio waves map hydrogen emissions. X-ray observations reveal hot gas. Gravitational measurements detect dark matter. Each method contributes a piece of the puzzle. The emerging picture shows a universe more structured and dynamic than anyone imagined a century ago. Galaxies do not drift randomly through space. They flow along well-defined paths shaped by dark matter distribution. They fall toward attractors and are pushed by voids. They participate in cosmic flows spanning hundreds of millions of light years. Our Milky Way follows one particular streamline in this cosmic river. We have been traveling along it for billions of years. We will continue for billions more before dark energy disrupts the pattern. Every second, we move 1,000 miles closer to the Great Attractor. That is roughly 400 million miles per year. Over 1 billion years, we travel nearly 500,000 light years. These distances exceed human comprehension. We evolved to understand the scale of forests and plains, not cosmic superclusters. Our intuition fails when confronting such vastness. Numbers lose meaning when they grow too large. Yet the universe exists at these scales, whether we can visualize them or not. The Great Attractor represents just one feature in a universe filled with similar structures. Other superclusters have their own attractors. Other voids create their own repelling effects. The cosmic web extends in all directions, organizing matter across the observable universe. What we have studied in detail is one small region of a far larger pattern. Scientists estimate that the observable universe contains roughly 2 trillion galaxies. Each participates in its own local flows. Each responds to nearby attractors and repellers. The complexity staggers imagination. Mapping all these motions would require measuring distances and velocities for trillions of objects. Current technology cannot accomplish that task. Yet we are trying. Each new survey extends our reach. Each improved instrument adds precision. Generation by generation, our maps become more complete. We are slowly revealing the architecture of the cosmos. The Great Attractor was just the beginning. More discoveries await beyond the horizon. Recent observations have revealed structures even larger than Laniakea. The Sloan Great Wall stretches across 1.4 billion light-years, containing tens of thousands of galaxies. Other walls and filaments span similar distances. These structures challenge our theoretical understanding of how the universe should be organized. According to standard cosmological models, structures above a certain size should not exist. The universe has only been around for about 14 billion years. Gravity needs time to pull matter together across vast distances. Structures exceeding roughly 1 billion light-years should be rare or impossible, yet observations keep finding them. This discrepancy has sparked debates among cosmologists. Some argue the discoveries indicate problems with standard models. Perhaps the early universe had stronger density fluctuations than we assume. Maybe dark matter behaves differently than current theories suggest. These possibilities would require revising fundamental aspects of cosmology. Others maintain that the large structures are not inconsistent with models. They point out that statistical fluctuations can create rare, unusually large formations. The observable universe is vast enough to contain such outliers. Finding them does not necessarily mean our theories are wrong, just that we are seeing the tail end of probability distributions. Resolving this debate requires better observations and more sophisticated simulations. Scientists need to map larger volumes of space to determine how common these massive structures truly are. Computer models must incorporate more realistic physics to see if they can reproduce the observations. The work continues. The Great Attractor fits comfortably within accepted theoretical limits. Laniakea, while large, does not exceed what models predict. The mystery surrounding it stems not from its size, but from its location. Being hidden in the zone of avoidance makes it difficult to study, creating uncertainty about its exact properties. Future telescopes will improve our view of this region. The Square Kilometre Array, a radio telescope network currently under construction, will map the zone of avoidance with unprecedented resolution. This instrument will detect hydrogen emissions from galaxies too faint for current telescopes to see. Hidden structures will emerge from the darkness. Space-based infrared observatories will complement ground-based radio surveys. Together, these instruments will create three-dimensional maps showing every galaxy within hundreds of millions of light-years. The Great Attractor will finally be revealed in full detail. We will know its exact mass, structure, and composition. These observations might answer lingering questions. Is the Norma cluster truly the core of the Great Attractor, or does another concentration hide deeper in the zone of avoidance? How much dark matter concentrates in that region? Do any unusual properties distinguish it from other superclusters? The answers wait for better data. Understanding the Great Attractor also helps test our cosmological models. By comparing observations with theoretical predictions, scientists can verify whether current theories accurately describe reality. If discrepancies emerge, we learn where our models need refinement. If observations match predictions, our confidence in those models strengthens. This process exemplifies how science progresses. Unexpected discoveries prompt new questions. Those questions drive improved observations. Better data either confirms existing theories or reveals where they fail. Failed theories get replaced by better ones. The cycle continues, gradually approaching truth. The Great Attractor played a key role in this process. Its discovery challenged assumptions about galactic motion. Finding it required developing new observational techniques. Explaining it demanded better understanding of dark matter and cosmic structure. Each challenge advanced the field. Similar discoveries await in other hidden regions. The zone of avoidance is not unique. Other parts of the sky remain poorly surveyed due to various observational difficulties. Each unexplored region might contain surprises that reshape our understanding. The universe is larger and stranger than we know. Our cosmic journey will end in isolation. This is a confirmed prediction based on well-established physics. Dark energy will continue accelerating universal expansion. Eventually, expansion will separate us from every structure outside our local gravitational neighborhood. The Great Attractor, the Shapley concentration, the dipole repeller, all will recede beyond the cosmic horizon. This fate seems bleak when stated plainly, yet it lies trillions of years in the future, far beyond timescales that affect any living thing. Stars will burn out long before cosmic isolation becomes complete. Galaxies will exhaust their gas supplies, ending star formation. The universe will grow dark and cold. Isolation will be the least of our problems in that distant era. For now, we inhabit a universe rich with structure and motion. We can observe cosmic flows. We can measure gravitational effects across hundreds of millions of light years. We can detect the pull of distant superclusters and the push of enormous voids. This era of observation will not last forever, but it is our era. Future astronomers will envy us. They will study ancient records describing a universe filled with galaxies and superclusters. Those structures will have vanished from their sky. Only theoretical calculations and historical archives will preserve knowledge of the cosmic web. They might wonder if the records are accurate or if ancient scientists misinterpreted their data. Yet, they will have their own discoveries to make. The universe always surprises us. Every era reveals new phenomena previously unknown. Our descendants, however distant, will explore mysteries we cannot imagine. They will develop technologies beyond our current capabilities. They will answer questions we have not thought to ask. The Great Attractor taught us that the universe operates at scales exceeding human intuition. It showed us that invisible forces shape cosmic destiny. It demonstrated that our galaxy participates in motions far larger than its own structure. These lessons will remain relevant no matter how the cosmos evolves. Understanding our place in this vast system provides perspective. Earth orbits one star among 200 billion in our galaxy. That galaxy is one among 100,000 in Laniakea. Laniakea flows towards Shapley among countless other superclusters. The hierarchy extends to scales we have barely begun to map. This perspective can be humbling or inspiring depending on your viewpoint. Some see insignificance in our cosmic smallness. Others see wonder in being part of such magnificent structure. Both reactions are valid. The universe does not care how we interpret our place within it. It simply exists, vast and strange and beautiful. The pull of the Great Attractor continues every moment. As you finish reading this sentence, you have traveled another 1,000 miles closer to it. The motion never stops. It has continued for billions of years. It will continue for billions more. We are passengers on a cosmic ship sailing through an ocean of space and time. Our journey has no visible destination. We chase structures that recede as we approach. Dark energy ensures we will never arrive. Yet the journey itself matters. Through motion, we are connected to the largest patterns in the cosmos. Through gravity, we participate in forces that span 500 million light years. The Great Attractor pulls us forward. The dipole repeller pushes us from behind. The expansion of space carries us along. These influences combine to determine our path through an evolving universe. We cannot change our trajectory, but we can observe it. We can measure it. We can understand it. That understanding represents humanity's greatest achievement, comprehending our place in the cosmos despite our cosmic insignificance. Cosmic flows behave like water moving across a landscape. Imagine rain falling on hills and mountains. Each drop follows gravity downhill, joining streams that merge into rivers. Those rivers flow toward valleys and lakes. The pattern emerges naturally from the shape of the land and the pull of gravity. Galaxies follow similar rules. They move through space along paths determined by the distribution of mass. Dense regions act like valleys, pulling material toward them. Voids act like hilltops, pushing material away. The cosmic web creates a gravitational landscape with peaks and valleys spanning hundreds of millions of light years. Scientists visualize these flows using streamlines, like meteorologists tracking air currents. Each streamline represents the path a galaxy follows over billions of years. When you trace these lines backward, they converge at specific points. Those convergence points mark the attractors, places where matter accumulates. The Great Attractor represents one such point. Think of a bathtub drain. Water swirls inward from all directions, creating a spiral pattern as it approaches the center. Galaxies near attractors show similar behavior. They accelerate as they get closer, pulled by ever stronger gravity. Multiple streams merge, creating larger flows. The pattern repeats at different scales throughout the universe. Mapping these flows requires measuring two things for each galaxy: distance and velocity. Distance tells you where the galaxy is located. Velocity reveals which direction it moves and how fast. Combine thousands of these measurements and patterns emerge. You can see which regions attract and which repel. The technique is called peculiar velocity mapping. Scientists measure how each galaxy moves relative to the overall expansion of space. If a galaxy moves faster toward one direction than expansion alone would predict, something must be pulling it. If it moves slower or in an unexpected direction, forces are influencing its path. These measurements are difficult. Small errors in distance estimates create large errors in velocity calculations. Imagine trying to measure the speed of a car by watching it from several miles away. Your margin for error is enormous. Astronomers face similar challenges when observing galaxies millions of light years distant. Yet by combining many measurements, accuracy improves. Errors in individual observations average out when you study hundreds or thousands of galaxies. The overall pattern becomes clear, even if specific details remain fuzzy. This statistical approach has revealed the flow structure of our local universe. The results show that Laniakea acts like a single gravitational basin. All the material within it flows toward the center, where the Great Attractor sits. The basin has boundaries where flows diverge instead of converge. Beyond those boundaries, galaxies belong to different basins and flow toward different attractors. Picture watersheds separating river systems. Rain falling on one side of a mountain ridge flows to one ocean. Rain falling on the other side flows to a different ocean. The ridge marks the boundary between two drainage basins. Cosmic structure works the same way. Laniakea is our drainage basin. The Shapley concentration forms a separate basin farther away. Where basins meet, strange things happen. Galaxies near the boundaries experience competing pulls from multiple attractors. Their paths become unpredictable, sensitive to small changes in initial conditions. Some galaxies might fall toward one attractor, others nearby might fall toward a different one. The boundary region creates cosmic chaos. The dipole repeller adds complexity to this picture. It acts like an upside-down valley, pushing material away instead of pulling it in. Flows diverge from its center, heading toward surrounding attractors. Our local group sits between the dipole repeller and the Great Attractor, caught between push and pull, Understanding these flows transforms how we think about cosmic structure. Radio astronomy opened windows into previously invisible regions of space. Unlike optical telescopes that detect visible light, radio telescopes capture long wavelength radiation. These waves pass through cosmic dust with minimal interference. Regions hidden to optical instruments become transparent to radio observation. The breakthrough came from detecting hydrogen emissions. Hydrogen atoms occasionally flip their electron spin, releasing energy as radio waves at a precise wavelength, 21 centimeters. This emission is a confirmed natural phenomenon occurring throughout the universe. By tuning receivers to this wavelength, astronomers can detect hydrogen anywhere, even behind dense dust clouds. Galaxies contain enormous quantities of hydrogen gas. Young galaxies especially hold vast reserves, fuel for future star formation. When radio telescopes map hydrogen emissions, they essentially map where galaxies exist. The technique works regardless of whether visible light can reach us. Hidden galaxies appear clearly in radio surveys. In the 1990s, astronomers began systematic radio surveys of the zone of avoidance. They expected to find some galaxies behind the dust. What they discovered exceeded predictions. Hundreds of galaxies emerged from regions thought to be empty. The true extent of cosmic structure in that direction had been severely underestimated. Two particularly significant galaxies were discovered in 1994 and 96. Named Dwingaloo 1 and Dwingaloo 2 after the observatory that found them, these galaxies are relatively nearby, at roughly 10 million light-years distance. Yet they remained completely unknown until radio surveys revealed them. They had been hiding in plain sight all along. More recent observations using advanced radio telescope arrays have found even more hidden structures. The Meerkat telescope in South Africa has proven especially valuable. Its 64 dishes work together, creating resolution far better than any single dish could achieve. Early results from Meerkat surveys revealed over 700 galaxies in the zone of avoidance, many previously unknown. These discoveries filled crucial gaps in maps of the Great Attractor region. Scientists could finally see what mass concentrations existed behind the obscuring dust. The Vela supercluster emerged as a major structure, containing thousands of galaxies previously hidden from view. This supercluster connects to the Norma cluster, extending the known boundaries of the Great Attractor. Radio observations also revealed something unexpected. The distribution of galaxies in the hidden zone looked different than predictions suggested. Some regions contained more galaxies than models anticipated. Other regions had fewer. These discrepancies hinted that our understanding of structure formation might need refinement. Think of completing a jigsaw puzzle after finding missing pieces under a couch. The overall picture makes more sense, but some pieces do not fit quite where you expected. Radio discoveries created similar surprises. They confirmed the existence of major structures while revealing unexpected details about their organization. The hydrogen emission technique has limitations. It detects only galaxies with substantial gas reserves. Old elliptical galaxies that exhausted their gas might remain invisible even to radio surveys. This creates selection bias in the observations. We might still be missing some portion of the galaxy population. Future radio observatories will push these techniques further. The Square Kilometre Array, currently under construction in South Africa and Australia, will be 50 times more sensitive than any existing radio telescope. It will detect hydrogen from galaxies billions of light-years away, even through the densest dust clouds. The entire zone of avoidance will become transparent to its instruments. These observations will create the first complete maps of our cosmic neighborhood. Every galaxy within hundreds of millions of light-years will be catalogued and measured. The true structure of the Great Attractor will emerge in full detail. Mysteries hidden for a century will finally be solved. The technology to pierce the cosmic veil exists. We simply need to finish building it. The cosmic microwave background radiation provides our most direct evidence for the Big Bang. This faint glow fills all of space, remnants of the moment when the early universe became transparent to light. The radiation comes from every direction, creating a nearly uniform bath of energy that pervades the cosmos. Nearly uniform, but not perfectly so. Tiny variations exist in the temperature of this background radiation. In one direction, the radiation appears slightly warmer. In the opposite direction, it appears slightly cooler. This pattern, called the dipole anisotropy, reveals something profound about our motion through space. Think of standing outside during a rainstorm. If you remain still, rain hits you equally from all directions. If you run forward, more raindrops hit your front than your back. The rain itself falls uniformly, but your motion creates an apparent imbalance. The cosmic microwave background works similarly. As we move through space, we encounter radiation differently depending on direction. Radiation from the direction we move toward gets blue shifted, making it appear warmer. Radiation from behind gets red shifted, appearing cooler. By measuring this temperature difference precisely, scientists can calculate our exact velocity through space. The measurements show we are moving at 631 miles per second toward a point in the constellation Hydra. This motion includes multiple components. Earth orbits our star. Our star orbits the galactic center. The entire Milky Way moves through space. All these motions combine to create our total velocity relative to the cosmic microwave background. Subtracting out the known motions reveals the galaxy's peculiar velocity. This is the extra motion beyond what universal expansion would predict. That peculiar velocity points almost directly toward the Great Attractor region. The alignment confirms that gravitational attraction is pulling us in that direction. The cosmic microwave background dipole was first detected in the 1970s. Scientists initially found a strong signal indicating motion, but they could not explain what caused it. The discovery of the Great Attractor in the 80s provided the answer. A massive concentration of matter in that direction was pulling us along. Precision measurements have refined the signal over decades. Modern satellites can detect temperature variations of millionths of a degree. They create detailed maps showing exactly how the background radiation varies across the sky. These maps reveal not just the dipole from our motion, but tinier fluctuations from the early universe itself. Those tiny fluctuations, imprinted when the universe was only 380,000 years old, seeded all structure we see today. Slightly warmer regions had slightly higher density. Gravity amplified those differences over billions of years, creating galaxies, clusters, and superclusters. The Great Attractor traces its origin to fluctuations visible in the cosmic microwave background. Scientists can compare the early fluctuations with current structures to test cosmological models. If the models accurately describe how the universe evolved, early fluctuations should predict where matter concentrates today. The match between predictions and observations is remarkably good, confirming our basic understanding of cosmic evolution. Yet mysteries remain. Some structures, like the Great Attractor, seem more massive than early fluctuations would suggest. The alignment between our motion and the predicted attractor location is not perfect. Small discrepancies hint that our picture might be incomplete. Perhaps additional attractors exist beyond what we have detected. Maybe the distribution of dark matter differs slightly from what models assume. These uncertainties drive continued research. Every improved measurement helps refine our understanding. The cosmic microwave background will continue providing insights for decades. Future satellites will map it with even greater precision. They will detect fluctuations too subtle for current instruments to see. Each new detail helps decode the universe's history. That ancient light still carries secrets about our cosmic destiny. Mapping the zone of avoidance resembles trying to chart terrain while standing inside thick fog. You know something exists beyond the obscuring veil. Instruments can detect hints of structure, yet creating accurate maps remains enormously difficult. Every observation comes with uncertainty. The fundamental problem is extinction. Dust particles scatter and absorb light, reducing the brightness of background objects. The more dust along the line of sight, the dimmer objects appear. After passing through enough material, light becomes too faint to detect. Objects effectively vanish into darkness. Scientists measure extinction by comparing how bright objects should appear with how bright they actually look. The difference indicates how much light was lost along the way. In the zone of avoidance, extinction can reduce brightness by factors of thousands or more. A galaxy that should shine brightly appears as a faint smudge or disappears entirely. Extinction varies with wavelength. Blue light gets scattered more than red light, which is why sunsets appear reddish. Looking through dust reveals the same effect. Blue stars look redder than they should. Red stars might remain visible while blue ones vanish. This wavelength-dependent extinction creates false impressions about what types of objects exist. Imagine trying to identify colored marbles through colored glass. The glass tints everything, making red marbles look different than they actually are. Blue marbles might appear purple or black. You would misjudge the true colors of everything you observe. Astronomers face similar challenges when viewing through dust. Correcting for extinction requires knowing how much dust lies along each line of sight. Scientists estimate this by measuring extinction to nearby stars and extrapolating to greater distances. Yet, the dust distribution is not uniform. Some regions are denser than others. Local variations create unpredictable effects. The zone of avoidance also suffers from stellar confusion. Our galaxy contains hundreds of billions of stars concentrated near the galactic plane. When you look toward the Great Attractor region, you look through this stellar foreground. Distant galaxies appear mixed with nearby stars. Separating them becomes difficult. Picture trying to spot boats on a distant lake while looking through a forest. The trees in the foreground block your view. When you glimpse the lake between branches, boats might be visible, yet telling boats apart from tree trunks at that distance proves challenging. Everything blurs together visually. Automated computer programs that scan images for galaxies struggle in the zone of avoidance. They get confused by the stellar foreground. Many stars appear similar in shape and brightness to small, distant galaxies. The programs generate numerous false detections, requiring human verification of each candidate. This verification process is slow and tedious. Astronomers must examine thousands of candidates by eye, deciding which are real galaxies and which are foreground stars. Even experienced observers sometimes guess wrong. Faint, fuzzy objects might be galaxies, or they might be unrelated artifacts. Uncertainty pervades the entire process. Despite these challenges, researchers have made remarkable progress. By combining observations at different wavelengths, they piece together a more complete picture. Optical surveys find galaxies in less obscured regions. Infrared observations penetrate deeper into the dust. Radio telescopes detect hydrogen regardless of extinction. X-ray satellites reveal hot gas from galaxy clusters. Each wavelength contributes unique information. Optical images show spiral structure and star formation. Infrared measurements estimate total stellar mass. Radio maps trace gas distribution. X-rays indicate cluster temperature and mass. Combining all these data creates three-dimensional models of hidden structures. Computer simulations help fill remaining gaps. Scientists input known galaxy positions and use physics to predict where additional galaxies should exist. These predictions guide searches in the most obscured regions. Sometimes the searches succeed, finding galaxies exactly where models predicted. Other times, predictions prove wrong, forcing model revisions. Progress comes slowly, one careful observation at a time. The zone of avoidance will never be completely transparent to our instruments. Yet, with persistence and clever techniques, scientists continue unveiling its secrets. The Great Attractor is emerging from the fog. We will never reach the Great Attractor. This is not speculation or uncertainty. The mathematics of cosmology makes this conclusion unavoidable. Universal expansion ensures that our destination recedes faster than we can approach it. Our journey has no endpoint. only eternal motion toward an unreachable goal. To understand why, consider how expansion affects cosmic journeys. Every second, new space appears between us and distant structures. This expansion adds to the distance we must travel. While gravity pulls us forward, expansion simultaneously pushes our target farther away. The two effects compete. For nearby structures, gravity wins easily. Andromeda approaches us despite expansion. Our local group will eventually merge into a single gravitationally bound system. Expansion is too weak at these distances to overcome attraction. The distance between us and Andromeda shrinks year by year. Yet at larger distances, expansion begins to dominate. The Great Attractor sits 200 million light-years away. At that distance, expansion creates significant separation velocity. Space between us and the Great Attractor expands at roughly 3,000 miles per second. Our infall velocity toward it reaches only a fraction of that rate. Think of walking up a down escalator. If you walk faster than the escalator moves, you reach the top. If the escalator moves faster than you walk, you can never arrive no matter how long you continue. The Great Attractor represents the second scenario. Expansion outpaces our approach velocity. Computer simulations tracking our future trajectory confirm this conclusion. They include both gravitational attraction and cosmic expansion. Over billions of years, we accelerate toward the Great Attractor, closing the distance significantly, yet we never arrive. Eventually, accelerating expansion reverses our progress. The distance begins increasing again. Dark energy drives this reversal. As the universe ages, dark energy becomes increasingly dominant. Its repulsive effect strengthens over time. Structures that currently attract us will eventually be pushed beyond our gravitational reach. The Great Attractor will recede beyond the cosmic horizon, disappearing from view entirely. This fate applies to all large-scale structures. The Shapley concentration will vanish. The dipole repeller will become undetectable. Even Laniakea will disperse as its component parts separate. Only our local group, merged with nearby galaxies, will remain gravitationally bound. Future inhabitants of our merged galaxy will observe a very different universe. Most structures visible to us will have vanished beyond the observable boundary. They will see only their local island of matter, surrounded by expanding emptiness. Evidence of the cosmic web will exist only in ancient records. Some scientists find this fate depressing. The universe appears headed toward cold, dark isolation. Stars will exhaust their fuel. Galaxies will grow dim. Eventually, even the merged remnants of galaxy groups will evaporate as stars are randomly ejected into intergalactic space. Others view it differently. The current era, rich with structure and motion, is special precisely because it is temporary. We inhabit a universe at peak complexity. The distant future holds less structure, but the distant past did too. Early in cosmic history, the universe was nearly uniform. Structure took billions of years to develop. We exist at a privileged moment. Cosmic structure is mature enough to observe yet young enough to remain connected. Future civilizations will envy our view. Ancient civilizations, if any existed, would have seen far less. This perspective makes our observations precious. The Great Attractor will never be visited, but it can be understood. We can measure its mass, map its structure, and comprehend its role in cosmic evolution. Understanding replaces physical arrival as the goal. Knowledge becomes its own destination. Our journey continues regardless of where it leads. Dark energy is tearing the universe apart. This process began billions of years ago and will continue indefinitely. Every second, the fabric of space stretches a tiny amount. Across cosmic distances, that tiny stretching accumulates into enormous separation. Nothing can stop it. Scientists discovered dark energy in 1998 through observations of distant supernovae. These stellar explosions serve as cosmic distance markers because they always shine with the same brightness. By measuring how bright they appear from Earth, astronomers calculate their distance. By measuring their redshift, they determine how fast they recede. The relationship between distance and recession velocity revealed something shocking. Distant supernovae were farther away than their redshifts predicted. The universe had expanded faster than models suggested. Instead of slowing down over time as gravity pulled everything together, expansion was accelerating. Something was pushing space apart with increasing force. This discovery overturned decades of assumptions. Scientists had expected universal expansion to decelerate. Early models predicted the universe would eventually recollapse into a big crunch, the opposite of the Big Bang. Other models suggested expansion would slow asymptotically to zero. None predicted acceleration. Yet multiple independent observations confirmed the result. Different teams using different telescopes all found the same pattern. The evidence became overwhelming. Universal expansion is accelerating, driven by some form of energy that permeates empty space. Scientists named this mysterious component dark energy. Think of dark energy as a property of space itself. Every cubic meter of vacuum contains a tiny amount of this energy. As the universe expands, new space appears. That new space brings additional dark energy. The total amount of dark energy in the universe increases over time. Its influence grows stronger. Dark energy behaves opposite to matter and gravity. Gravity attracts, pulling things together. Dark energy repels, pushing things apart. Currently, dark energy accounts for roughly 70% of all energy in the universe. As expansion continues, that percentage will increase further. Dark energy will become even more dominant. The effects of dark energy strengthen with distance. Nearby galaxies feel minimal influence because the volume of space between us is small. Distant galaxies experience much stronger effects because more space separates us. This distance dependence explains why dark energy barely affects our local group but dominates at supercluster scales. Laniakea cannot resist dark energy indefinitely. The supercluster is not gravitationally bound. Its components flow together now because they are still falling into gravitational wells. Yet expansion opposes this inflow. In several billion years, expansion will overcome the attraction. Laniakea will begin dispersing. First, the outer regions will separate. Galaxies on the periphery will stop flowing inward and begin receding. The boundaries of Laniakea will contract as outlying material escapes. The structure will shrink, containing fewer galaxies within its gravitational basin. This process will continue until only the densest core remains bound. Eventually, even the core will succumb. Dark energy will push component clusters beyond each other's gravitational reach. The Great Attractor region will fragment into separate pieces. Each piece will drift away from the others, isolated by expanding space. The cosmic flows that currently connect us will cease. This fate extends to all structure in the universe. Superclusters will disperse. Clusters will fragment. Some galaxy groups might survive temporarily, but even they face eventual disruption. Only structures held together by forces stronger than dark energy will endure. Our local group represents such a structure. Gravity binding the Milky Way and Andromeda is strong enough to resist dark energy. The merged galaxy resulting from their collision will remain intact indefinitely. Any smaller galaxies captured by our gravity will also survive. Together, they will form an isolated island. Trillions of years from now, that island will be all that remains visible. Everything beyond will have receded past the cosmic horizon. The observable universe will shrink to just our local gravitational neighborhood. Observers will see almost nothing when they look into space. Dark energy will continue operating even then, stretching space relentlessly. Recent surveys have revealed that Laniakea might be part of something even larger. The Shapley concentration appears to form the center of an enormous basin of attraction that includes our supercluster. This discovery, announced in the early 2020s, extended our cosmic address once again. Scientists studied galaxy flows across unprecedented distances, mapping over 1 billion light-years of space. The data showed that Laniakea, Apus, Hercules, and several other superclusters all appear to be moving toward the Shapley region. These flows suggest a gravitational basin 10 times larger than Laniakea itself. Think of Laniakea as a tributary feeding into a much larger river system. The Great Attractor marks where streams within Laniakea converge. Those streams then join the broader flow toward Shapley. Multiple superclusters contribute to this massive current, creating a structure of staggering proportions. The Shapley Basin would contain over 1 million large galaxies spread across several billion light-years. That volume approaches the limits of what current surveys can map. Measuring flows at such distances requires extreme precision. Small errors in velocity measurements create large uncertainties in the reconstructed flow patterns. Yet multiple independent analyses reached similar conclusions. Different teams, using different methods, all detected the flow toward Shapley. The consistency of results provides confidence that the structure is real. We appear to inhabit not just a supercluster, but a supercluster spanning a significant fraction of the observable universe. This discovery challenges theoretical predictions. Structures this large should barely exist according to standard cosmological models. The universe has only been around for 14 billion years. Gravity needs time to organize matter into coherent structures. Creating something as massive as the Shapley Basin requires longer than the age of the universe suggests. Perhaps the early universe had larger density fluctuations than models assume. Maybe dark matter clumped more efficiently in some regions than others. These possibilities would allow larger structures to form faster. Yet, they require adjusting parameters in ways that might conflict with other observations. Alternatively, what appears as a single basin might actually be multiple structures that happen to align from our perspective. Imagine seeing 3 hills in a row that look like one long ridge. From another angle, they would clearly be separate. Cosmic structure might create similar illusions when viewed along certain directions. Resolving this uncertainty requires observations from different cosmic locations. Since we cannot physically move to other galaxies, we must use clever techniques. Studying how structures appear from different angles as we observe at different distances provides some perspective. Computer simulations also help by showing what various configurations would look like from our viewpoint. The Shapley concentration itself is confirmed to be real and massive. It contains thousands of galaxies in dozens of clusters. The concentration represents one of the largest structures unambiguously identified in the universe. Whether it anchors an even larger basin remains an open question. If the Shapley Basin exists as described, it would make the Sloan Great Wall seem modest. That structure, stretching 1.4 billion light-years, currently holds the record for largest confirmed cosmic structure. The Shapley Basin would exceed it significantly in both size and mass. Future surveys will map larger volumes with greater precision. The Dark Energy Spectroscopic Instrument, currently operating in Arizona, will measure distances and velocities for tens of millions of galaxies. That data will reveal flow patterns across unprecedented distances. The true extent of super-large structures will become clear. Each discovery pushes the boundaries of known structure. Each new level of organization raises questions about what exists at even larger scales. The hierarchy might extend beyond what current instruments can observe. Structures larger than the Shapley Basin might exist, simply too big for us to detect yet. The universe grows stranger the farther we look. Scientists debate what mechanisms create structures as massive as the Great Attractor. Several competing theories attempt to explain how such concentrations of matter arise. Each theory makes different predictions that observations can test. The true explanation might involve combinations of multiple mechanisms. The standard model relies on dark matter as the primary structure-forming agent. In this picture, dark matter begins clumping shortly after the Big Bang. Tiny quantum fluctuations in the early universe create regions slightly denser than average. Dark matter unaffected by radiation pressure, can collapse into these regions immediately. Regular matter follows later, falling into the gravitational wells that dark matter creates. This process works well for explaining galaxy formation and cluster assembly. Computer simulations based on this model successfully reproduce the cosmic web. They create filaments, clusters, and voids that match observations. The Great Attractor emerges naturally as one concentration among many in a universe dominated by dark matter. Yet the model struggles with the largest structures. Simulations typically produce superclusters smaller than what observations reveal. The Shapley Basin, if real, exceeds predicted sizes by significant margins. This discrepancy suggests either the initial conditions were different than assumed, or additional physics affects structure formation. Some scientists propose that primordial black holes might contribute to structure formation. These hypothetical objects would have formed in the first fractions of a second after the Big Bang. If primordial black holes exist, they could serve as additional seeds for structure formation. Their gravity would attract dark matter and regular matter more efficiently than density fluctuations alone. This theory remains speculative. No confirmed evidence for primordial black holes exists, yet the idea has merit because it could explain anomalously large structures. If concentrated populations of primordial black holes existed in certain regions, they would create gravitational wells deeper than standard models predict. The Great Attractor might mark such a concentration. Another possibility involves cosmic strings, hypothetical defects in the fabric of space-time. These would have formed during phase transitions in the early universe, similar to how cracks form in freezing ice. Cosmic strings would have enormous linear mass density, creating powerful gravitational effects along their length. Galaxies could accumulate along these strings like beads on a thread. Cosmic strings could explain filamentary structures in the cosmic web. They might create the long walls and filaments where galaxies concentrate. The Great Attractor could represent a junction where multiple strings intersect. Yet, like primordial black holes, cosmic strings remain undetected. Their existence is theoretical, not confirmed. Modified gravity theories offer a different approach entirely. These theories suggest that gravity behaves differently at cosmic scales than Einstein's equations predict. If true, structure formation would follow different rules. Large concentrations might arise more easily than standard models suggest, explaining the Great Attractor without requiring dark matter. However, modified gravity struggles to explain other observations. The cosmic microwave background radiation patterns, gravitational lensing measurements, and galaxy rotation curves all point toward dark matter rather than modified gravity. Most scientists consider dark matter more likely, though modified gravity remains an active area of research. Hybrid models, combining several mechanisms, might prove necessary. Perhaps dark matter provides the foundation, while primordial black holes or cosmic strings enhance certain regions. Or maybe our understanding of dark matter itself needs refinement. Different types of dark matter particles might behave differently, affecting structure formation in ways current models do not capture. Testing these theories requires better observations. Precise measurements of the cosmic microwave background can constrain initial conditions. Detailed maps of dark matter distribution reveal how structure formed. Galaxy surveys at different cosmic epochs show how structure evolved over time. Each new piece of data helps discriminate between competing explanations. The Great Attractor serves as a test case for our theoretical understanding, explaining how it formed and why it exists where it does challenges cosmological models. Any successful theory of structure formation must account for objects like the Great Attractor. The truth likely involves physics we barely understand. The universe expands forever. This is the most likely fate based on current observations. Dark energy will continue accelerating expansion indefinitely. Billions of years from now, the cosmos will be very different from what we observe today. Understanding our ultimate destiny requires projecting physics forward across timescales that dwarf human experience. Over the next 100 billion years, Star formation will continue but gradually decline. Galaxies will exhaust their gas reserves, the raw material for new stars. Each generation of stars converts hydrogen into heavier elements. Eventually, the fuel runs out. Stellar nurseries will grow dark and silent. Our galaxy will merge with Andromeda long before this happens. That collision, occurring in roughly 4 billion years, will trigger a final burst of star formation. Gas clouds will collide and compress, igniting millions of new stars. After this burst fades, the merged galaxy will slowly consume its remaining fuel. Around the same time, our star will evolve into a red giant. It will swell enormously, possibly engulfing Earth's orbit. The outer layers will blow away, leaving behind a dense white dwarf surrounded by a planetary nebula. Billions of stars throughout the galaxy will follow similar evolutionary paths. By 1 trillion years from now, most stars will have burned out. The universe will contain mostly dead stellar remnants, white dwarfs, neutron stars, and black holes. The rare stars still burning will be small red dwarfs, sipping fuel so slowly they last for trillions of years. Galaxies will glow faintly with their dim light. Dark energy will have dispersed most large-scale structure by this point. The local group merger will remain bound, but everything beyond will have receded past the cosmic horizon. Observers will see only their local galaxy surrounded by darkness. The cosmic microwave background will be stretched to undetectable wavelengths. Evidence of the Big Bang will have vanished. Expansion continues relentlessly. By 10 to the 15th power years, even red dwarfs will have exhausted their fuel. The last natural light in the universe will flicker out. Galaxies will contain only dead stars, slowly evaporating as random gravitational interactions eject stars into intergalactic space. Galaxy remnants will dissolve into scattered stellar corpses. Black holes will dominate the far future. These objects grow by consuming material that wanders too close. Over immense timescales, black holes might merge with each other, forming larger and larger examples. Eventually, a few supermassive black holes might be all that remains of once great galaxies. Yet even black holes do not last forever. Stephen Hawking showed that black holes slowly evaporate through a quantum mechanical process. They emit radiation, losing mass over time. Small black holes evaporate relatively quickly. Supermassive ones take longer, but even they eventually disappear. By 10 to the 100th power years, all black holes will have evaporated. The universe will contain only elementary particles scattered across expanding space. Electrons, positrons, neutrinos, and photons will drift through the void. The temperature will approach absolute zero. Nothing happens anymore. The universe enters what scientists call the heat death. This represents ultimate entropy, maximum disorder. No energy gradients exist to drive processes. No stars shine. No structures persist. The universe has reached thermal equilibrium at the coldest possible temperature. Time loses meaning when nothing changes. Yet uncertainty remains even at these extreme timescales. Perhaps protons decay, breaking down matter into pure energy. Maybe vacuum fluctuations create new matter occasionally. Quantum mechanics might allow rare events to occur even in the heat death. The universe could persist in this state forever, with unimaginably rare fluctuations the only occurrences. Some theories suggest new universes might spontaneously nucleate from the vacuum. Quantum tunneling could create bubble universes that expand into new spacetimes. Our universe might be one bubble in an eternally inflating multiverse. Other bubbles exist beyond our cosmic horizon, forever unreachable but equally real. These ideas venture beyond what observations can currently test. They represent extrapolations of known physics into regimes where uncertainty dominates. Yet, they demonstrate how cosmology forces us to think about the deepest questions. Why does the universe exist? Where did it come from? Where is it going? The great attractor is pulling us somewhere we will never reach. Dark energy ensures our journey has no conclusion. We travel through an expanding universe toward an unreachable destination. Our galaxy will eventually drift alone through an increasingly empty cosmos. Stars will die. Structures will dissolve. Everything returns to cold darkness. Yet, for now, we race through space at over 1 million miles per hour. We participate in cosmic flows spanning hundreds of millions of light years. We are connected to structures of unimaginable size. We inhabit a universe rich with complexity and motion. This moment, this era, will not last forever. That makes it all the more precious. The pull continues, the journey goes on, and somewhere in the darkness, the great attractor waits. The first hints of our cosmic motion came from unexpected sources. In the early 1900s, astronomers noticed something strange about galaxy distributions. Certain regions of the sky contained far more galaxies than others. The pattern seemed too organized to be random chance. Vesto Slipher, working at Lowell Observatory, began measuring galaxy velocities in 1912. He used spectroscopy, splitting galaxy light into component wavelengths. By comparing these wavelengths to laboratory measurements, he could detect shifts, indicating motion. Almost every galaxy showed a redshift, meaning they moved away from us. Yet the redshifts were not uniform. Some galaxies receded faster than others at similar distances. This violated what simple expansion models predicted. If the universe expanded smoothly, galaxies at the same distance should recede at identical rates. The variations suggested additional motion beyond universal expansion. Think of boats on a lake during a windstorm. Some drift with the wind while others fight against it. Their actual speeds differ from what wind alone would produce. Galaxies showed similar behavior. Something beyond expansion influenced their motion. By the 1930s, scientists had measured hundreds of galaxy velocities. Harlow Shapley noticed that many galaxies in one region showed peculiar motions, all pointing the same direction. He called it the Shapley concentration, though he could not explain what caused the pattern. The technology to understand this phenomenon would not exist for decades. The breakthrough required better distance measurements. Astronomers needed to know exactly how far away each galaxy was located. Redshift alone was insufficient because peculiar velocities contaminated the measurements. Independent distance indicators became essential for progress. Cepheid variable stars provided one solution. These stars pulse regularly, brightening and dimming over predictable periods. The period directly relates to the star's intrinsic brightness. By measuring the period and comparing it to the apparent brightness, astronomers could calculate distance. This technique worked for relatively nearby galaxies where individual stars could be resolved. For more distant galaxies, scientists used type Ia supernovae. These stellar explosions always reach roughly the same peak brightness. Measuring how bright they appear reveals their distance. Combining supernova distances with redshift measurements allowed scientists to detect peculiar velocities across vast cosmic distances. By the 1970s, enough data existed to map large-scale motions. Sandra Faber and her colleagues analyzed galaxy velocities across millions of light years. They found coherent flows spanning enormous distances. Hundreds of galaxies moved together like a cosmic river. Something massive had to be pulling them. The Seven Samurai, a team of astronomers in the 1980s, refined these measurements dramatically. They studied elliptical galaxies, measuring relationships between their properties. Combining multiple indicators improved distance accuracy. Their maps revealed flows extending farther than anyone expected. These flows converged toward a specific region hidden behind the Milky Way. The team calculated that something with the mass of tens of thousands of galaxies occupied that location. Alan Dressler named it the Great Attractor in 1987. The name captured both the mystery and the magnitude of the phenomenon. Early reactions were skeptical. Many astronomers doubted that such a massive structure could hide so completely. Perhaps the measurements were wrong. Maybe the calculations contained errors. The zone of avoidance made verification nearly impossible. Yet, independent teams using different methods reached identical conclusions. The motion was real. The mass concentration existed. Our galaxy was falling towards something we could not see. The evidence became overwhelming despite the observational challenges. This discovery transformed cosmology. It revealed that the universe contained structures far larger than previously imagined. It showed that our motion through space involved more than simple expansion. It proved that enormous concentrations of matter could remain hidden from optical surveys. The search to understand the Great Attractor had begun. Modern astronomy depends on technology that would seem like magic to early observers. Telescopes now operate in wavelengths invisible to human eyes. Computers process data at speeds that allow analyzing millions of galaxies simultaneously. Spacecraft orbit beyond Earth's atmosphere, avoiding the distortion that air creates. Each advance reveals cosmic details previously hidden. The Hubble Space Telescope revolutionized deep space observation. Launched in 1990, this instrument orbits above the atmosphere where air turbulence cannot blur images. Its mirrors, while relatively small compared to ground telescopes, achieve unprecedented clarity. Hubble has photographed regions of the zone of avoidance in visible and near-infrared wavelengths. Yet even Hubble struggles with the densest dust clouds. The James Webb Space Telescope, operating since 2022, goes further. Webb observes primarily in infrared wavelengths, where dust becomes nearly transparent. Its massive mirror collects faint light from objects billions of light-years away. Early observations have already revealed previously hidden galaxies in obscured regions. Think of infrared astronomy like using thermal imaging cameras. These devices detect heat rather than visible light. They reveal warm objects even in complete darkness. Webb functions similarly, detecting the heat signature of distant galaxies. Dust that blocks optical light allows infrared through with minimal interference. Ground-based telescopes have evolved dramatically as well. Adaptive optics systems compensate for atmospheric distortion in real time. These systems use deformable mirrors that change shape hundreds of times per second. By correcting for air turbulence, they achieve resolution rivaling space telescopes. Major observatories now routinely employ this technology. Radio astronomy provides another crucial tool. The Very Large Array in New Mexico combines 27 dishes into a single instrument. Together, they create resolution equivalent to a telescope many miles wide. Similar arrays exist in Chile, Australia, and other locations. These instruments map hydrogen emissions from galaxies, regardless of dust obscuration. The Meerkat Array in South Africa represents the cutting edge of radio astronomy. Its 64 dishes work together with extraordinary precision. The telescope can detect hydrogen from galaxies hundreds of millions of light-years away. Recent surveys using Meerkat have uncovered hundreds of galaxies hiding in the zone of avoidance. Future instruments promise even greater capabilities. The Square Kilometre Array, currently under construction, will be 50 times more sensitive than existing radio telescopes. It will map the entire zone of avoidance in unprecedented detail. Hidden structures will emerge from the darkness, like stars appearing at twilight. X-ray observatories add another perspective. Hot gas trapped in galaxy clusters emits X-rays as it heats to millions of degrees. The Chandra X-ray Observatory and XMM Newton satellite have mapped X-ray emissions from the Great Attractor region. These observations reveal the locations of massive clusters. Even when optical light remains blocked, gravitational wave detectors represent an entirely new observational window. These instruments detect ripples in space-time caused by colliding black holes or neutron stars. While not directly observing the Great Attractor, Gravitational wave astronomy provides information about mass distribution throughout the universe. Future detectors might reveal structures through gravitational effects alone. Supercomputers process the enormous data volumes modern telescopes generate. A single night of observation can produce terabytes of information. Computers analyze each galaxy image, measure brightnesses, calculate distances, and determine velocities. Algorithms search for patterns humans would never notice manually. Machine learning enhances this analysis further. Computer programs trained on millions of galaxy images can automatically classify new observations. They distinguish galaxies from stars with accuracy exceeding human observers. They detect faint structures in noisy data. They find rare objects among millions of common ones. Combining data from multiple instruments creates three-dimensional maps of cosmic structure. Optical surveys provide galaxy positions. Infrared observations measure stellar masses. Radio telescopes trace gas distributions. X-ray satellites reveal hot plasma. Gravitational measurements indicate dark matter concentrations. Together, these create a comprehensive picture. The technology continues advancing. Each generation of instruments surpasses the previous one. Telescopes grow larger. Detectors become more sensitive. Computers process data faster. Our view of the hidden universe improves year by year. The Great Attractor cannot hide forever. Individual stars care nothing about cosmic flows. A typical star like ours orbits the galactic center, completing one revolution every 225 million years. During our journey toward the Great Attractor, our star will complete dozens of orbits. Each orbit follows nearly the same path regardless of the galaxy's overall motion. Think of passengers on a ship. They walk around the deck, unaware the ship is crossing an ocean. Their movement relative to the ship matters more than the ship's movement through water. Stars behave similarly. They orbit within the galaxy, while the galaxy itself travels through space. Yet our cosmic journey will eventually affect stellar orbits. When the Milky Way collides with Andromeda in 4 billion years, gravitational chaos will scramble everything. Stars will be flung onto new paths. Some will be ejected entirely, cast into intergalactic space. Others will spiral toward the merged galaxy's center. The familiar structure of spiral arms will be destroyed. Computer simulations model this collision in extraordinary detail. They track millions of simulated stars through the merger process. The results show tidal tails stretching hundreds of thousands of light years. Long streams of stars arc away from the collision site. These tails persist for billions of years before dispersing. Our solar system will likely survive intact. The odds of another star passing close enough to disrupt planetary orbits remain vanishingly small. Space between stars is so vast that direct encounters almost never occur. We will probably emerge from the collision unscathed, simply relocated to a different part of the merged galaxy. Some stars will not be so fortunate. Close passes, while rare, do happen during galactic mergers. A star passing within a few light years could gravitationally perturb planetary orbits. Planets might be ejected from their systems or sent spiraling into their stars. Entire solar systems could be destroyed by near misses. More commonly, stars will find themselves in unfamiliar neighborhoods. A star currently in the outer disk might end up near the galactic core. Another might be flung to the distant halo. The galaxy will be thoroughly mixed, erasing all previous structure. Future astronomers will find no trace of where their star originally orbited. The merger will trigger massive star formation. Colliding gas clouds will compress, creating conditions for new stars to ignite. Regions that were quiet for billions of years will blaze with newly born stars. These stars will be hot, massive, and short-lived. They will burn brilliantly for a few million years before exploding as supernovae. Those supernovae will enrich surrounding space with heavy elements. Carbon, oxygen, iron, and other elements forged in stellar cores will be scattered through the interstellar medium. Future generations of stars forming from this enriched material will contain higher metal content. Planets orbiting those stars might be more likely to develop life. Yet the merger also ends star formation in the long term. The collision will consume much of the available gas. What remains will be heated too hot to collapse. After the initial burst fades, star formation will nearly cease. The merged galaxy will slowly age as existing stars burn out without being replaced. This fate awaits all galaxies in our local group. The merger will create a single elliptical galaxy containing all the stars from both spirals. Some astronomers have named this future galaxy Milkomeda. Others prefer Milkdromeda. Whatever we call it, the structure will differ fundamentally from either parent galaxy. Elliptical galaxies lack spiral arms and disk structure. Their stars orbit in random directions rather than following organized paths. They contain mostly old red stars with little gas for forming new ones. Elliptical galaxies represent the endpoint of galactic evolution, the final form that emerges from mergers. Our solar system will orbit within this elliptical galaxy for billions of years after the merger. The view from Earth, if it still exists, will be dramatically different. The night sky will contain far more stars visible to the naked eye. The galactic core will dominate, a brilliant bulge of ancient stars. No spiral arms will grace the sky. This transformation happens while we continue our journey toward the Great Attractor. The merger and the cosmic flow occur independently, driven by different forces at different scales. Our participation in both demonstrates how multiple processes shape cosmic destiny simultaneously. Stars are just passengers on a much larger journey. The Great Attractor is not unique. Similar structures exist throughout the observable universe, each pulling nearby galaxies toward them. The Perseus-Pisces supercluster forms another major concentration, roughly 250 million light-years from Earth. The Coma supercluster sits in a different direction at similar distance. Each represents a node in the cosmic web. These structures share common properties. All contain thousands of galaxies organized into multiple clusters. Dense concentrations of dark matter create deep gravitational wells. Hot gas trapped between galaxies emits X-rays detectable across vast distances. The patterns repeat throughout the universe at different locations. The Shapley concentration dwarfs them all. Located 650 million light-years away, this structure contains roughly 10 times more mass than Laniakea. Dozens of rich galaxy clusters crowd into a relatively small volume. The combined gravitational pull affects cosmic flows across billions of light-years. Think of Shapley as a cosmic drain where multiple river systems converge. Material from surrounding regions flows toward it from all directions. Laniakea appears to be falling toward Shapley along with several other superclusters. The combined motion suggests an even larger structure organizing flows at unprecedented scales. Beyond Shapley lies the Sloan Great Wall. This structure stretches across 1.4 billion light-years, making it one of the largest known cosmic formations. Unlike compact superclusters, the Sloan Great Wall forms a sheet of galaxies extending through space. It represents a filament in the cosmic web, connecting multiple smaller concentrations. Discovering such structures required surveys mapping millions of galaxies. The Sloan Digital Sky Survey photographed large portions of the sky, measuring distances and positions for enormous numbers of objects. When astronomers plotted the three-dimensional distribution, walls, filaments, and voids emerged clearly from the data. The cosmic web extends as far as telescopes can observe. Every survey reveals similar patterns. Galaxies cluster along filaments, nodes mark where filaments intersect, voids occupy the spaces between. The structure appears fractal, showing similar patterns at different scales. Small clusters resemble large superclusters, which resemble even larger structures. This organization emerged from the early universe through gravitational amplification of tiny fluctuations. Regions slightly denser than average pulled in more material. That increased their density further, strengthening their gravity. Over billions of years, the process created the structures we observe today. Computer simulations reproduce this evolution remarkably well. Starting from initial conditions matching the cosmic microwave background, simulations create virtual universes. Dark matter clumps first, forming the scaffolding. Regular matter follows, settling into the gravitational wells. After billions of simulated years, the result matches real observations. These simulations predict that structures similar to the Great Attractor should be common. Every large volume of space should contain multiple superclusters organized around central attractors. The Great Attractor is simply the one closest to us, making it easiest to detect and study. Yet some observed structures exceed what simulations typically produce. The Shapley Basin, if confirmed at the size suggested by recent observations, would be unusually large. The Sloan Great Wall also appears more extensive than simulations commonly create. These discrepancies hint that our models might miss some aspect of structure formation. Perhaps the initial fluctuations varied more than standard models assume. Maybe dark matter behaves slightly differently than we think, or cosmic strings, primordial black holes, or other exotic physics might enhance structure formation in ways current simulations omit. Testing these ideas requires better observations across larger volumes. The Dark Energy Spectroscopic Instrument currently conducts the most ambitious galaxy survey ever attempted. It will measure distances to tens of millions of galaxies, mapping cosmic structure across half the observable universe. Results should reveal whether unusually large structures are rare outliers or common features. Other great attractors exist beyond what we have detected. The observable universe extends roughly 46 billion light-years in all directions. Most of that volume remains unmapped. Countless superclusters likely exist in unexplored regions, each organizing local flows around their gravitational centers. The universe is larger and more structured than we can fully comprehend. We drift through an incomprehensibly vast universe, pulled by forces we cannot see toward destinations we will never reach. This realization carries profound implications for how we understand our existence. Everything familiar exists within a galaxy that is itself just one droplet in a cosmic ocean. Consider the scales involved. Earth orbits an average star in the outer regions of a typical spiral galaxy. That galaxy contains 200 billion stars, most with their own planetary systems. Our galaxy belongs to a small cluster of a few dozen galaxies. That cluster flows through a supercluster containing 100,000 large galaxies. The supercluster participates in even larger flows towards structures billions of light-years away. At each level, we become increasingly insignificant, yet simultaneously we become increasingly connected. The same gravitational forces that bind atoms into molecules and planets into solar systems also bind superclusters into even larger structures. We are part of an unbroken hierarchy extending from the quantum to the cosmic. This perspective transforms how we think about meaning and purpose. Religious and philosophical traditions often place humanity at the center of creation. The cosmos revolves around our concerns in these worldviews. Modern astronomy reveals a different picture. We occupy no special location. We participate in no unique processes. Everything we consider important happens on a tiny planet, orbiting an ordinary star in an unremarkable galaxy. Some find this disturbing. If we are so cosmically insignificant, how can our lives have meaning? If the universe neither knows nor cares about our existence, why should anything matter? These questions have troubled thinkers since we first understood our cosmic situation. Yet others find liberation in the same realization. We are free to create our own meaning precisely because the universe imposes none. Our significance to each other need not depend on cosmic importance. The connections we form, the knowledge we discover, the beauty we create all matter, even if they matter only to us. The Great Attractor will pull our galaxy across hundreds of millions of light-years. Yet this cosmic journey affects human life Not at all. We live, love, work, and die on timescales of decades. Cosmic motion operates on timescales of billions of years. The two realms barely interact. Think of bacteria living in a drop of water on a leaf. The leaf grows on a tree in a forest that covers a mountain. The mountain sits on a tectonic plate drifting across Earth's surface. Each level of organization exists independently. The bacteria's life means everything to the bacterium but nothing to the mountain. The mountain's motion means everything to geology but nothing to the bacterium. We resemble those bacteria more than we might prefer to acknowledge. Our concerns operate at human scales. Cosmic flows matter to cosmology, but not to daily existence. Recognizing this disconnect provides valuable perspective. Problems that seem overwhelming often shrink when viewed against cosmic context. Yet we possess something the bacteria lack: the ability to comprehend the larger context. We can understand our cosmic situation even while remaining bound by human limitations. This understanding represents something genuinely remarkable. The universe has, through us, developed awareness of itself. We are how the cosmos knows it exists. Stars cannot contemplate their fate. Galaxies cannot wonder about their origins. Dark matter remains eternally unconscious of its own presence. Only through complex structures like human brains does the universe achieve self-reflection. This grants meaning to our existence, whether or not we occupy a cosmically important location. We are the universe observing itself, measuring itself, trying to comprehend itself. Every discovery we make, every question we answer, represents the cosmos coming to understand its own nature. The Great Attractor pulls us through space. We map its structure and measure its mass. We calculate its effects and predict its future. Through our observations, something unconscious becomes known. Through our understanding, meaningless motion acquires meaning. We will never escape our cosmic insignificance. The forces shaping the universe will continue whether we exist or not. Dark energy will keep accelerating expansion. Galaxies will disperse into isolation. Stars will exhaust their fuel and fade. None of these processes care about humanity. Yet while we exist, we observe. While we observe, we understand. While we understand, we give meaning to what would otherwise remain forever meaningless. The Great Attractor exists as a fact of cosmology, that we know it exists, that we study it, that we tell stories about it, transforms it into something more. Our cosmic journey continues, pulling us somewhere we will never arrive.